So we're going to continue working with angle relationships in circles. Remember, the key thing that we talked about earlier was to look for where the vertex is. So we're going to look at different diagrams. So you're going to see secants, chords, tangents create more angles, but again, the key thing is where is the vertex. So even though this is not what we call an inscribed angle because it's not made from two chords or two secants, now we have an angle that's created by a secant and a tangent line. The vertex is still on the circle, so it still has the exact same relationship. So if a tangent and a secant, or a tangent and a chord, intersect a circle, oh, that's circle, at a point on the circle, then the measure of the created angle is 1/2 the measure of the intercepted arc. So it has the exact same relationship as the inscribed angle. So the measure of angle ABC, is going to be 1/2 of the arc that it intercepts. And you'll see it intercepts this arc from A to B, right? That's the part that's kind of inside the mouth of that angle. Okay, so if we take a look at example 1, here's where things might look a little confusing. We have a whole bunch of angles, we have a whole bunch of lines, chords, secants, whatever, right? Tangents hitting the circle. Make sure you still just bring it back to what individual angles are we looking at. We're going to assume anything that looks like a tangent is a tangent. So a point of tangency would be F and a point of tangency would be G. Okay, we're going to look for two things. Let's look for the measure of angle, EFH, and let's also look for the measure of angle, HFG. Okay, so let's start by looking for the measure of angle EFH. So just like before, look at where the vertex is, and F is on the circumference of the circle, which means that angle should be 1/2 of whatever its intercepted arc is. So if we follow the vertex out to E and out to H, you should see that the intercepted arc is this 130 degrees. So pretty straightforward. The measure of angle EFH should be 1/2 of that arc, FH. So we're just going to take 1/2 of 130. So that should give us 65 degrees. So if you look at part B, then we're trying to find the measure of angle HFG. So this might be a little more involved, but once again, where is that angle, the vertex of that angle? It's on the circle. So we know that this angle, which happens to be an inscribed angle that we talked about in the last lesson, is going to be 1/2 of its intercepted arc. And this time the arc goes from H to G. But the big question is, what does that arc measure? Because we don't have anything written there. So think about it. What do you think we're going to do to find that missing arc measure? Well, remember, a full circle is 360 degrees, and we have a linear pair. So if I called this angle FGI, for example, how do I find the measure of angle FGI? Well, a linear pair adds up to 180, so 180 minus 122 gives me that angle measure, which should be 58 degrees. And then remember, the angle G here has a vertex on the circle, so that means it's 1/2 of the intercepted arc, FG. So if I double 58, I know that that arc from F to G is 116 degrees. Right, so then I can use the 116, the 130 to find HG because I know a full circle is 360. I'm going to do 360 minus 130 minus 116. So that arc is 114 degrees, which means coming back to that original inscribed angle theorem, the measure of angle HFG is 1/2 of 114, which is 57 degrees. Okay, so we just want to be okay with looking at multiple relationships, just adding in the new angle relationships we're learning. We're going to do one more in this video, and that'll be it. We'll finish the rest in class. So the second theorem now deals with an angle with a vertex, notice now, in the interior of the circle. Make sure you notice this is not necessarily the center. It could be the center, but it doesn't have to be, so we don't want to assume anything. So this theorem says if two secants or chords intersect in the interior of a circle, then the measure of each angle formed is 1/2 the sum of the intercepted arcs. Okay, so again, we don't want to assume that E is in the center. It could be if BC and DA happen to be diameters, but if they're not, that's okay, because what we're going to do is look at the intercepted arcs. So if we focus on angle 1 here, you'll notice two things. There's actually vertical angles, so angle 1 is congruent to angle CED as well. And we're going to use those two intercepted arcs on the two sides of those vertical angles. So the measure of angle 1 is going to equal 1/2 the sum of the two intercepted arcs opposite of angle 1. So it's going to be the measure of arc AB plus the measure of arc CD. Alternatively, if we want to find, let's say, measure of angle 2, which is AEC that I just wrote in there, that's vertical to angle DEB. So then we'd be looking at these arcs instead, AC and BD. So the measure of angle 2 would be 1/2 the measure of arc AC plus the measure of arc BD. Okay, so that's our second theorem. So if you take a look at example 2, I want to find the measure of angle AEB. So first identify, where is angle AEB? AEB is this big one right here. So then what are the intercepted arcs that go with it? Well, hopefully you're seeing definitely AB, but then you also want to see, okay, what's vertical to AEB? Well, that's here on the bottom, DEC, and use the arc that corresponds to DEC as well. So I'm going to use that information to set up my equation. So the measure of angle AEB is going to equal 1/2 of the arc measure of AB plus the measure of arc DC, and then just plug it all in. These theorems don't have any nice names to go with them, so remember, if you're using them in a proof, just abbreviate, summarize as well as you can. Okay, so just make sure you have your PEMDAS done correctly. 113 plus 139, that's going to give us 252, and then divide that by 2 to get 126. All right, and remember that angle is not a central angle because it's not the center. It's just somewhere in the interior, right? Unless you specifically see that we have a dot in the middle, or you're told that these are all diameters, or use the name of the circle, don't assume it's a center. Okay? So in our last relationship that we're looking at today, we're looking at, you'll see below we have 3 different situations, but they all involve a secant. So you have a secant, tangent, a secant, secant, or a tangent, tangent. And what's important is you notice for all 3 of these angles, the angle is actually outside of the circle. So that's what we're kind of looking at, is where the vertex is. So for all 3 cases here, the angle is outside, and we have 3 different ways we can make that angle outside when we have a secant tangent, a tangent tangent, and a secant secant. So now what's this relationship? It says that basically if a tangent and a secant, 2 tangents or 2 secants intersect in the exterior of a circle, then the measure of the angle formed by it is 1/2 the difference of the intercepted arcs. So let me go ahead and jot that down. All right, so once again, basically if we have two segments or lines, right, intersecting outside of our circle, and those segments happen to be two tangents, two secants, or a secant and a tangent, then the measure of the angle formed is going to be 1/2 the difference of the intercepted arcs. So when we're talking about the intercepted arcs, what we're looking at are the arcs that are inside the angle. So if you look at this very first angle, angle 1, we have two intercepted arcs. One is AD, because you can see that's the outer arc, right? And then the other arc here is going to be BD. So if I were to look for the measure of angle 1, it's equal to 1/2 the difference of arc AD and BD. We want to go bigger to smaller, outside minus inside. So that's what that means by we're looking for the difference of the intercepted arcs, okay? So it's the same for every situation, right? If you look here in the middle for angle 2, we have two intercepted arcs. One here is EHG, and then the other is EG. All right, so the measure of angle 2 equals 1/2 the measure of the major arc EHG minus the inner arc, right, the minor arc EG. Now something important you want to realize in this specific situation with two tangents, you'll notice if you put together the two arcs I've highlighted, the intercepted arcs, what do you get? Well, we're getting a whole circle, which means these two arcs should add up to 360. So that means for this particular case, you don't actually have to have both arc measures. All I have to do is give you one, and to find the other, you do 360 minus the given. So if I told you EG was 100 degrees, then you automatically know EHG is 260 because they add up to 360. And that's only, again, when it's two tangents. All right. This third one, angle 3, same as before. You're going to look at that angle, look at the two arcs that are inside the angle. We've got one that goes from J to N, and we've got another that goes from K to M. And to solve for the measure of angle 3, we're just going to do 1/2 the outer arc, JN, minus the measure of the inner arc, KM. And that's our last relationship, okay? So if we take a look at example 3A, we can basically apply it. And what you're looking for, remember, is where is the vertex, right? This vertex E is outside the circle. So that's how I know, okay, I'm going to do 1/2 and then subtract the arcs. Versus if it was inside, then I'm going to do 1/2 and add the arcs, right? So that's kind of how I remember which relationship to use as I look at the vertex. So I can go ahead and set up my equation. It really doesn't matter if it's a secant, tangent, 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 secant, secant, because it's all going to be the same formula, right? This measure of angle DEF is going to be 1/2 the difference of the intercepted arcs. And what are those intercepted arcs? I'm going to follow the angles out. I'll see one arc at the outside is CG, and the inner arc here is DF. So this will be 1/2 of arc CG minus arc DF, because we're going to go outer minus inner, and then just plug it all in. So X is 1/2 of 87 minus 7. 1/2 of 80 is 40. All right, so go ahead and try part B, just making sure we can apply the theorem. All right, and there we go. So hopefully we all got 63. And we can see again, it's because we set up our equation by doing the difference of the two arcs and then divide it by 2, because this angle is outside the circle. So just to kind of summarize, we have multiple angle relationships. If the angle has a vertex on the center, the measure of the angle equals the measure of the arc, right? If the angle's vertex is on the actual circle, that's the inscribed angle, right? Then the measure of the angle is 1/2 the measure of the arc. If our angle is in the interior but not the center, we're going to do 1/2 of the sum of the two intercepted arcs. And then this last one, if our angle's outside, it's going to be 1/2 the difference of the two intercepted arcs. So 4 different angle relationships we want to keep straight. And it all depends on where the vertex is. So that's what I would always look for, is where the vertex is. So finally, we can put it all together and look at kind of a larger situation going on. And we're looking for here the arc, the measure of arc YZ.
And as always, when you do any kind of larger problem, any kind of proof, right, any kind of problem solving, we want to start with making sure we know what we're looking for. So where is arc YZ? So YZ is this kind of large arc here on the right. And then what I would do is I would start thinking, okay, what are some relationships I can do with this arc YZ? And then I might start looking for something that looks doable to me. So for example, I might notice, okay, YZ, I can trace it back to this angle X. So then I can say, hey, well, the measure of angle YXV is 1/2 the measure of arc YZ minus, and then I can call this point, let's say A, some other point, right? Minus the measure of arc YA. So that's one possible relationship, okay? Then you might be looking and you saying, wait a minute, I also see this situation. I can trace back from Y down to V and V to X to also create that intercepted arc. And now this angle is in the interior. So I could also say, well, hey, we also have this relationship that the measure of angle YVZ is 1/2 the sum of arc YZ plus arc AW, right? So those are basically two starting points I would kind of take out from the situation. And then I would start thinking about, well, what would be easier for me to find, right? I happen to know what the angle measures here are for YXV and YVZ. So I'm just deciding which one's easier to find, arc YA or arc AW. And that's going to help me decide which one of those two equations to use, right? So we always want to have options in mind, but kind of narrow it down to one path. And then what I'm going to notice here is, wait a minute, the problem also tells me arc WZ. So if I have arc WZ, I can kind of bring that back and make a relationship with this angle WVZ. And then I might realize, wait a minute, I've got a linear pair right here. So I can figure out angle WVZ is 180 minus 113. And then why would that be important? Hopefully you guys are kind of seeing where I'm going with this. 180 minus 113, which gives me 67. Why would I want that? Because if this angle right here is 67 degrees, I can look at that interior angle, right? It's not at the center, but it's in the inside, and say, hey, the measure of angle WVZ happens to be 1/2 the sum of the two intercepted arcs, which are WZ and AY. And look, AY, YA, same thing. That's what I want. And I happen to know this angle WVZ is 67. The problem tells me arc WZ is 68. So I'll just call this YA to be consistent. And I can find my one missing piece of information to actually help me get to the arc YZ. So that's what you also want to look for, is look for other relationships. You'll see how I put together a linear pair with that other angle relationship with the vertex inside my circle. And then now I'm going to use that with that last theorem with my vertex outside to find my missing arc. So there's a lot going on here that we have to process. But if you start looking for a missing piece, right, you can work your way backwards to figure out other relationships. All right, so let's go ahead and finish this off. So I'm going to multiply both sides by 2 to get rid of the 1/2. If you want to distribute the 2, you can too, but I like to get rid of the fraction sooner than later, if I could. So that's going to be 134. And then I'm just going to subtract the 68 to get 66 degrees as the measure of the arc YA. And now that I have YA, I'm not going to use that second equation. I'm going to use that first one because I found the YA rather than AW. And I know that the measure of angle YXV is 49. So I'm going to substitute 49 in. I'm looking for YZ, so leave that as an unknown. And then plug in 66. And once again, I'm going to multiply by 2 because I like to get rid of the fraction first. So then I'm going to get 98. and then add the 66 to both sides to get 164 as the measure of that missing arc YZ. All right. Would it be wrong if you used that red equation? No, it's a perfectly fine relationship. I just happen to use the pink one because I found YA a lot easier to find first. If you can find AW, go for it. It's going to give you the same answer. Okay? So really think about those kind of multi-step problems, and hopefully you're looking at where the vertex is to come up with the relationships with these angles and arcs in our circles. All right, so let me know if you have any questions. Thanks for listening.